Welcome back to the video lecture series for Introduction to Data Programming using Scala. In the last video, we looked at sequential search. Sequential search is a very basic search. It'll work on any collection of items that you want, and that makes it powerful. It's also very easy to write, as we saw. However, it has the downside that it is not very efficient. Okay, and so if you're going to be doing lots and lots and lots of searching, a sequential search is not the way to do it, especially if your data set is large. So in this video, we're going to introduce an alternate form of searching, the binary search. Now, the thing about a binary search is that, unlike the sequential search, it only works on sorted data. Okay, so the flexibility that we had with the sequential search of working on anything we wanted, that goes away. Okay. The analogy that I often give to students is if I hand you a phone book. In fact, I find this analogy somewhat funny because I know that within a few years my students won't know what a phone book is because no one uses them anymore. But hopefully the people watching this video at this point will still have at least seen a phone book, even if you never actually had to use one. If I hand you a phone book and I tell you to look someone up by their name, you're perfectly happy to do it. And the reason is because the phone book is sorted by names. On the other hand, if I hand you a phone book and I tell you to look up someone by their phone number, that's not so nice, especially if you live in a large metropolitan area where the phone book has has a million or more entries in it. And there again, the reason is because it's not in sequential order, or it's not in sorted order. If you look something up in a phone book by telephone number, you have to do a sequential search because you have no ordering for it. If you look something up in a phone book by name, then you can use a binary search. And what you do isn't exactly a binary search, but what humans do in a telephone book will actually be pretty close to what we're going to do with our binary search. So, but once again, it requires that the data is sorted. This search does not work. And of course, if you want to use it and you have unsorted data, you have to sort your data first. And the sorting has a big cost. So this is really only worthwhile if you're going to be doing lots of searches. Though in many applications, that's exactly what you do. You sort it once, and then you search many, 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 many different times. So let's look at the way the binary search works. So I'm going to start here with the array that we had previously when demonstrating our sorts, and it's at this point been sorted for us. And the way binary search works is it has a range of the array that it's looking at, and it takes the midpoint. And it asks the question, well, first, is this what we're looking for? If the midpoint is what we're looking for, we're done. Okay. If the midpoint is not what we're looking for, then it asks the question, is what we're looking for less than or greater than this value? And at that point, it throws away half of the array. Okay. So, for example, if I was looking for the value 2, I would look at the 5. 2 is not 5, so I know it's not here. And then I would say, well, 2 is less than 5. So it turns out I can immediately rule out not just the 5, but I can rule out everything to the right of the 5. And so now I know that it has to be down on this half. And then I repeat that same process. I pick the thing that's in the middle. In this case, it will be the 3. It kind of depends upon exactly how the integer math goes for what indices you're keeping. So I have the 1, 2, and 4. I have an index 0 and 4. So it'll give me index 2, which is here at the 3. And it will say, is 2 equal to 3? No. So is it less than or greater than? It'll be less than again. And so then we throw away not just the 3, but we throw away the 4 as well. And we come here. So then we just have the 1 and the 2. And so you can see how this process works. We're continually throwing away half of the array that's left. So we can illustrate what we're going to do in the code. I like to keep two variables, start and end, that keep track of the whole range that I'm looking over, and then a variable called mid, which is the average of the two. And so in this example, if my start is here and my end is here, my mid will wind up referencing there. Now you might wonder, why the heck is your end pointing out into the middle of nowhere? It is often a standard convention when talking about ranges on an array or a list to give an endpoint that is exclusive. So the beginning is inclusive and the end is exclusive. And in this case it helps because our integer division truncates. So if you use an end that's not exclusive, you can occasionally set up situations where, if you're not careful, you have an infinite loop, because your mid winds up being equal to the start or the end in a way that it shouldn't be. So once again, here I would do my comparison. Let's say this time I was searching for 7. Okay, so what exactly would happen? Well, if I was searching for 7, I would say, well, 7 is not 5. And so I would then ask, is 7 less than or greater than 5? Because 7 is greater than 5, I take my start value and I point it to be 1 bigger than the mid. Why 1 bigger? Well, because the start value is inclusive, and I know it's not the 5, and I know it can't be anything to the left of the 5. So it has to be there. And then I would take the midpoint of these two, and that becomes my new mid. And I repeat the process. And we repeat, and we repeat, and we repeat. So let's see what this looks like if we write it in code. So we have our sequential search. I am going to go ahead and write the binary search. And once again, I'll do an array events. Now, I actually want to write binary search kind of in 2 ways. In this video, I'll just write it the first way, where I'm going to use a loop. We can also write a very nice binary search recursively, and so we'll do that next. So I'm going to create my variable. Start is 0. End is a dot length. Remember, so the array does not go up to this index, but I want my end to be exclusive. And then mid equals start plus end over 2. While what? There are 2 situations at which I could terminate. One would be if a sub mid is equal, whoops, I need another argument here, don't I? I need to pass in what I'm looking for. If the mid is what I am looking for, well, then I should stop. So I want to keep going while a sub mid is not what I'm looking for. And I also need to have it so that I stop if at any point start is greater than or equal to end. Okay. So let's go back to our picture here. What if we were looking for something that wasn't in the array? Well, if we were looking for something that wasn't in the array, eventually we should get to a situation that looks like this. Okay. And because the inside is exclusive, we know that it's not part of what we're searching for. This is basically an empty situation. If somehow our math got us into a situation where these things were crossed over, that would also indicate that what we're looking for is not present. So what happens inside of this while loop? Well, we know that it's not mid because of this. So I need to ask if a sub mid, so if what I'm looking for, if it's less than a sub mid, well, then I set end equal to mid. Remember, end is exclusive. I've just ruled out mid, so I want the end to actually be equal to mid. Else, if it's not equal and it's not less than, well, then it has to be greater than. And so I don't edit the end, I edit the start, and the start is equal to mid plus 1. Because as we talked about, the start side is inclusive, and we've ruled out mid, so we need to move 1 beyond it. After we've done that, we simply reassign mid to be start plus end over 2, and repeat, repeat, repeat. There are 2 possibilities when we're done here. So either a sub mid is equal to looking for, in which case we return mid. Otherwise, we return -1. We could also express this as saying if start is less than end. And in fact, depending upon what it is that you were searching for, that might be a better criteria because it's definitely comparing integers. Whereas if this were an array of strings, for example, an equality check can be less efficient. So now I have it's 3yy. I need to test this code. Now I can't just test this code as this is written here. Why not? Well, because nums is not a sorted array. If you use a binary search on an array that's not sorted, you get back gibberish. You will get back something that is completely irrelevant, because I would look here at the middle and I say, is the thing I'm looking for greater than or less than this? Well, what if I was looking for a 9? Well, it would say, oh, the 9's greater than, and it would move to this half of the array. But of course, the 9's over on this side. So the values really have to be in sorted order for this to be meaningful. And I'm going to create a little variable called snums, which is the sorted version of nums. And I'm going to use the API call for sorting because I don't feel like copying in our sort code here. And let's see if I have that written correctly. Oops. Yeah. Insert int equals. Apparently I did do that correctly up there. Because I didn't tell it, I said that it returned unit, so it printed out unit for all of those. We're getting all negative ones. Okay, so this is a good example. Now we have to do some debugging because the 4 and the 7 definitely appear in this array, and so we should be finding them. So this implies that we never got a submid equal to what we're looking for, and what I would like to do is put in a print line here of start plus mid plus end. Well, isn't that interesting? So, I want to keep going while start is less than end. I did that same problem here because I was describing it using words that were, so 2, 6, and -1. Now, of course, the question is that correct? Let's print out our array so that we can check this. We could also compare it to the results of a regular search. So first we were looking for the 4, 0, 1, 2, okay, yep, index 2, 2. Then we were looking for a 7, 3, 4, 5, 6. Sure enough, there's a 7 at index 6, and the 2 wasn't found. Just to test this out, let's also look for the 43 to make sure that we can go up on the high side. Yes, I erased a parentheses there. Okay. 13. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. And there you go. Okay, so we've written our binary search. We have, this is a binary search uses a while loop. It's reasonably easy to write, though as you saw, I managed to mess up my conditions and therefore have a bug the first time, so it definitely needs some testing. We'll come back in the next video and we'll look at an alternate approach to the binary search, and we'll also talk about just how fast a binary search is.